All right, thanks everyone. Morning everyone. So I'm Jordan. I'm a second year PhD student at ICRA UWA, and I'm going to be talking to you about cosmic star formation and AGN activity over 13 billion years. So extragalactic objects I can broadly categorize into sort of two camps using things like the BPT diagram shown here. On one hand, I have the star forming things, which are generally gas rich and, as the name suggests, actively forming stars. And on the other end, I have these things that are called active galactic nuclei, or AGN, thought to be or understood to be the central components of a galaxy, generally a supermassive black hole, accreting matter and outputting a whole mess of energy into the galaxy. Now, in analyses of star formation, often the approach is just to cut out all of the AGNs out of the sample to mitigate things like AGN contamination. Indeed, this was the approach that was taken in Drivers and others 2018 in their analysis of the cosmic star formation history. Very quickly, cosmic star formation history, you basically look at all the star formation in the universe in a volume slice and you plot that as a function of redshift or look back time shown here. So in this work, they use a combination of the mid-infrared and radio luminosities to select out the AGN. And they varied this selection to put a maximum uncertainty on the cosmic star formation history of about 0.1 dex. While it's encouraging that because of this selection, you don't get this huge uncertainty, the more pressing issue with this approach is that you can never reconcile the interface of AGN and star formation activity and how they fit into the life cycle of galaxies. Why do we care about this? Well, we care because we know that the AGN affect the properties of the host galaxy. An example of this is what I'm showing, is what I'll show here. So this is the star formation rate stellar mass plane. And the blue outline here is the locus of these points, often known as the main sequence of star formation. The thing that I want to draw your attention to is the dispersion in the star formation main sequence shown by the green error bars here. So towards low stellar masses, you see that there's an increase in the dispersion, which is thought to be driven by stellar feedback and stochastic star bursts. There's a minimum in the dispersion at about 10 to the 10 solar masses of stellar mass. But at high redshift, at high stellar mass, it starts to increase again. And the driver of this increase in dispersion is thought to be because of AGN feedback. So as I said earlier, AGN inject a whole mess of energy into the galaxy. They inhibit star formation at high stellar masses and drive galaxies down in this plane towards low stellar mass, in this way driving this sort of asymmetric scatter. So clearly, if we want to know something about galaxy formation and star formation, we also would like to know something about what the AGN is doing to quench that star formation and how that affects that. So all of these things, how the AGN and star formation fits in galaxies has a signature on the light distribution of these galaxies, as you can see in this sort of toy model of a galaxy here. So what we want to do is we want to have some sort of tool that allows us to model the contribution to the light distribution, or SED, from both stars and AGN. And this is what the SED fitting tool Prospect can do. Essentially, Prospect asks the question, what physical properties would a galaxy need to have in order to produce its observed light distribution at so many different wavelengths? And in doing so, can solve for things like the stellar mass, the star formation rate, and the AGN luminosity. So Prospect was used to fit the SEDs, light distributions, for a whole bunch of galaxies in the Gamma and Devils D10 catalogs, and work that was first presented by Thorne and others 21 and 22, and also Belsat and others 2020. So to look at star formation and AGN activity in the universe, what we do is we follow the approach of Driver and others in 2018 and calculate the cosmic star formation history. And this is our result here. I don't know why my uncertainty quantiles are gone, but they are there in the paper. So you see what we find is that star formation starts at a minimum towards the early universe. So the early universe is going left towards higher look back times here. It peaks at around 10 gigayears or so and been declining ever since. And I don't know where my driver points has gone, but we do agree with the driver points. Sorry about that. And we also agree quite well with the McDowell-Dickinson 14 result, which is the sort of standard candle for this cosmic star formation history. I'll remind you that this is self-consistently accounting for the AGN and the AGN component and the stellar component in the SEDs. So to look further into the AGN, we can basically do a very similar exercise with the AGN luminosities. Look at all the AGN luminosity, add them together, plot that as a function of time. And we get this plot here, all the magenta points and lines. So we get something that looks pretty similar to the cosmic star formation history. It starts at a minimum, it peaks and been declining ever since. And we exhibit broad agreement with the Richards, some other previous literature results shown by the black line. Now, to look at the interface of these two things, we can take those two lines and divide them together and plot that as a function of time, and we get this result here. And our main finding is that cosmic AGN and star formation activity have been roughly coeval over the last 11 billion years. So to try and interpret this a little bit, what we do is we look at the median stellar masses of the galaxies that contribute most to the cosmic star formation history, given by the points in the error bars, and compare them to the median stellar masses of the galaxies contributing most to the cosmic AGN luminosity history, given by the points, and I promise you they're supposed to be there, the error quantiles. And we find that they are very similar. So it's the similar kinds of galaxies contributing to both of these things. In other words, the thing that is causing the declines of both the cosmic star formation history and AGN luminosity history below about 10 gigayears likely comes from the same origin and is operating at the same rate. An obvious sort of candidate to interpret this is simply the depletion of the gas supply. So we just learned, just like the zooxanthellae and coral feed on the sunlight, galaxies feed on the gas in their galaxies. And the galaxies feed on the gas inside of them. And the same gas that is feeding stars is also the same gas that is fueling the central black hole and powering the AGN. So as the gas supply is consumed, both of these things, AGN and star formation activity, wind down equivalently to ensure that they are roughly coeval over the last 11 billion years. So that's kind of like the main result of my project one of this work, and all of this has been submitted in a paper. We just got a really good review report yesterday, so keep your eyes peeled on the archive for that published work soon. Now you'll notice in all of these plots, there's this hatchbox region, which is telling you that we can't really trust the results out to there. So with gamma and double Z10, we can basically push this analysis up to about redshift 5, which I think is basically the local universe still at this point. Because of selection effects, and as I said, we can't really trust the data back then. So the next step is then to tackle this with high redshift observations with the James Webb Space Telescope. So I probably don't have to introduce this. I'm sure everyone's really fed up with seeing this image, but this is the Joe Biden cluster. What we've been doing over the last year is trying to apply our novel techniques and imaging processing techniques to get the most out of this data. So this is the released image, and this here is our best efforts. Now, as a more technical example, I'm showing you an example of these artifact removals that we've been busy working on. This is WISP artifact removal, 1/f artifact removal. So while JWST is probably blowing your mind, there is so much, still so much stuff to do with it, and a lot of quirks with the instrument that we have to sort out. So here's an example of this in published work as well. Now, we've made all of these improvements and efforts on doing the data reduction. How about I show you some science? So I'm very excited to share with you these preliminary results from our JWST imaging. So this is the star formation main sequence, the star formation rate stellar mass plane between redshift 5 and redshift 11.4, calculated for 106 spectroscopically confirmed high redshift galaxies in the Sears survey. So basically what we did was we looked at the JWST photometry, combined them with Hubble Space Telescope photometry, and fit the 12-band SEDs with Prospect to get the star formation rates and stellar masses. And I'm showing here some 2 independent simulation lines, so basically theoretical predictions on the star formation main sequence in work that I published earlier this year. Okay, so some key points. So basically, we found that AGN and star formation activity has been roughly coeval for the last 11 billion years. And I guess going forward, what we'll do is we'll try and look at this interface of star formation and AGN activity in the first galaxies to have ever formed in the with JWST that formed within the first few gigayears after the Big Bang. Yeah, and I think that's all I wanted to say. Thanks for listening.